Assalamu alaikum. Welcome to this lesson on analyzing loops and nested structures. In this module, we'll explore how to evaluate the efficiency of code involving loops, one of the most common sources of time complexity in any algorithm. You learn how to estimate how long loops take to run and how nesting or structure impacts performance. When we analyze an algorithm, loops are often the first thing to inspect. Why? Because they repeat, and repetition means more computation. Our job is to figure out how many times will this loop run, and if we scale the input, how does that affect runtime? We'll look at common loop patterns, single, nested, triangular, logarithmic, and build the tools to estimate time complexity using Big O. Let's start simple. A fixed count loop shown here. Even though this is a loop, it always runs exactly 1000 times, no matter what the input is. Each iteration does a constant time operation, a square root and an addition. So overall, this is Big O of 1, or constant time. The cost never changes with input size. In real life, this is like counting out exactly 1000 tickets. Doesn't matter how big the audience is, you're only doing 1000 operations. Now we move to a loop that depends on n. This one clearly scales with the size of n. If n is 10, it runs 10 times. If it is 10,000, it runs 10,000 times. Again, the operation inside is constant. So the complexity is Big O of n, which is linear time. If you are scanning a list or processing each record in a file, you are typically seeing linear complexity. Here's an interesting variation. This loop could end early if the target is found. In the best case, it stops after one iteration. That is big omega 1, constant time. But in the worst case, the target is lost or not present. So it goes through all n items. That is Big O of n. Even if a loop includes break, we still focus on worst case for Big O, unless told otherwise. Now let's examine nested loops. Here the outer loop runs n times. For every iteration of I, the inner loop also runs n times. That is n cross n operations, or Big O of n square, which is quadratic time. This pattern appears often in brute force comparisons, like checking all pairs in a list or comparing rows in a matrix. We can further extend this. Now, this particular code performs the operation in n cross n or n cube times. That's Big O of n cube, which is known as cubic time. These kinds of loops show up in 3D data processing or advanced simulation code, but they are rare because they get expensive very fast. Here's a more subtle case. The inner loop doesn't go from 0 to n. It depends on I. So the total number of comparisons is n plus 1, n plus 2, so on and so forth until it reaches 1, which is equivalent to n into n minus 1 divided by 2. Once we simplify it, it is Big O of n square. This was the example we saw in the previous lecture as well. So you'll see this sort of loop being used in sorting algorithms like bubble sort, or anywhere we are comparing unique pairs. Now, loops can have different bounds too. The total work depends on both n and m. So the complexity is Big O of n cross m. This is very common in matrix processing, or algorithms where input comes in rows and columns, or outer or inner lists. One of the most powerful patterns, this loops, keeps halving n. If you start at 16, you get 16, then 8, then 4, then 2, eventually 1. This is just 4 steps. Each time you divide by 2. So this loop runs log with base 2 of n times. That is, the Big O is log of n. Very efficient and common in binary search, tree operations, and divide and conquer algorithms. Now we have an outer loop that runs log n times and an inner loop that runs n times. So total complexity is n cross log n. This is the sweet spot for efficient algorithms like merge sort or heap sort. It is faster than quadratic, but more powerful than linear. That's it for analyzing loops. Next, we'll apply these same techniques to recursion, where the repetition is hidden inside function calls. See you there.